Okay, hello class. Welcome to Physics 390 class 11. This class will be on the first part of our treatment of the hydrogen atom. It's chapter 4.1 of the textbook. This is where we'll establish the three-dimensional Schrodinger equation. We'll look at spherical coordinates because the hydrogen atom potential is only depends on the distance from the origin, making spherical coordinates the most natural choice. And then we'll look in general at if we have what's called a central potential, how to solve the time-independent Schrodinger equation for the three different, we're going to do a separation of variables and see what that looks like. So this is the first part of our solution to the hydrogen atom. Okay, so the Schrodinger equation in three dimensions. Well, the time-dependent Schrodinger equation in three dimensions looks a lot like the one in one dimension, except that instead of the partial with respect to x squared here, we have this del squared here, which is called the Laplacian. And that's a sort of a three-dimensional version of the second derivative with respect to x. So the Laplacian, the form of the Laplacian depends on the coordinate system. So in Cartesian coordinates, x, y, z, we have the Laplacian is the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. So this is a very convenient generalization of the first derivative, second derivative with respect to x that we see in one dimension. We just add the second derivative with respect to y and with respect to z, the other coordinates, to what we have in one dimension to get three dimensions. In spherical coordinates, because spherical coordinates, the relationship between the coordinates is a little more complicated than for Cartesian coordinates. For example, in Cartesian coordinates, a little step in what we call a length vector is just dx, dy, dz. Whereas in spherical coordinates, a little step in space is dr, r d theta, r sine theta d phi. So the concept of length involves all three variables. So for that reason, the Laplacian here is more complicated in spherical coordinates. And again, we're interested in spherical coordinates because the hydrogen atom is most naturally expressed, the potential is most naturally expressed in spherical coordinates. So, okay, so that's the time-dependent Schrodinger equation. But the one we solve is the time-independent Schrodinger equation. And that looks, again, very much like, that's right here. That looks very much like the time-independent Schrodinger equation in one dimension. Except again, we have this del squared, the Laplacian, instead of dd or partial with respect to x squared, or in this case, d dx squared, because there's only one variable here. There's no time variable. So that's the generalization as we replace the partial with respect to x squared with the Laplacian to go from 1 to 3 dimensions. We still get a complete orthonormal set of stationary states when we solve the time-independent Schrodinger equation, the PHYS, lowercase psi n of r, and n being the index for the stationary states. And what we mean by orthonormal, just to review, is that the inner product of psi m and psi n, which would be given by this integral of psi m star psi n over now the volume element, since we're in 3 dimensions, would be equal to delta mn, meaning that if m is equal to n, we have the normalization integral for psi n, which would give 1. If m is not equal to n, then these two are orthogonal and we get 0. So this expresses orthonormality. And the completeness, as you might remember, is expressed by the sum over all the stationary states of the projection operators, psi n ket, psi n bra, over all of those projection operators being equal to 1. So that expresses the completeness, that this is a complete set, and any function can be expressed as a superposition of all of these, a combination of all of these stationary states. So so the time dependence doesn't really change. The time dependence, once we have the stationary states, lowercase psi n of r, and this bold r means vector, then the time dependent wave function will be the stationary state times the exponential time dependence e to the minus I ent over h bar, which will depend on n. So some of them oscillate, the higher the energy, the faster they oscillate in time. And the complete solution will be psi r of t will be the sum over these time-dependent states weighted by coefficient Cn. And in general, those Cn can be found from the wave function at time zero, psi r0. We can find the weights from the initial wave function at time zero, and then this gives the time dependence for all time. Okay, so that's kind of how the Schrodinger equation generalizes from 1 to 3 dimensions. A lot of similarities, just again, the Laplacian coming in is the main difference. Okay, so central potentials and separation of variables. So again, most physical potentials of interest depend only on R, like in the hydrogen atom, because if we have a proton and an electron, the potential energy between them only depends on the distance between them, r. I don't mean the vector r, I mean the distance r. So the potential energy only depends on how far away the electron is from the, the proton at the nucleus of the hydrogen atom. Other potentials, the harmonic oscillator in 3 dimensions depends only on r. A spherical well with 0 inside a sphere and infinity outside a sphere, the potential depends only on r. So they're spherically symmetric potentials, which are most potentials have that symmetry. So because of that, we most often use spherical coordinates, okay, because that has r as a variable. And that's the most leads, even though the equations we get will be somewhat complicated, they'd be even more complicated in Cartesian coordinates. So we like working in spherical coordinates. So the time-independent Schrodinger equation for a potential V that depends only on R, so-called central potential, is this right here. So this is minus h bar squared over 2m times the Laplacian of psi. So we've just plugged in the formula, which we looked at just a minute ago for the Laplacian applied to psi, plus v psi is equals e psi. So that's the time-independent Schrodinger equation. Okay, so fairly involved. So we're going to have to be smart about the way we approach this. And that's part of what we're going to look at for the rest of this video. So divide and conquer. When in doubt, try separation of variables. So we take this function psi, which is a function of r, theta, and phi in this equation here, and we divide it up into a function only of r, capital R of r, and a function only of theta and phi, capital Y. Okay, a radial function and an angular function. And let's see. So inserting psi is equal to r times y into this equation everywhere for psi, and doing some algebra and rearrangements takes a few steps. Please see the textbook for the detailed steps. I'm not going to go through those here, but it leads to a separation. We are able to successfully separate variables, separate the r variable from the theta and the phi variables. And this is what we get. We get the this expression for the function capital R, and with the variable the radial variable r is equal to a separation constant, which is written as L times L plus 1 which seems a little funny, but it's written that way for later convenience. It turns out to make some formulas that come out of the analysis of the hydrogen atom and the central potentials look nicer. So that's why it's a little bit strange. We don't just call it like Q or some other just single variable. We call it L times L plus 1. And so that's the radial equation. The angular equation looks like this when we separate, and it's equal actually to minus the separation constant. And one thing to notice is that the angular equation does not depend on the particular potential V of R. Notice V of R only appears in this radial equation here. There's no V in this one. So that means that no matter what the central potential we have, no matter what V of R is, we still have the same angular equation. So we can solve the angular equation in general for the central potential, and the solutions we get will apply no matter what we have for V of R, as long as V is a central potential and depends only on the distance R. So all these, the 3D harmonic oscillator, the hydrogen atom, the 3D spherical well, as I was talking about, and several other potentials have the same angular dependence. So that's kind of nice. Okay, so let's look at that angular dependence, the angular equation for central potentials, V of R. Here's this equation again for the separated angular function y. So again, it's simpler than the first equation we had involving all three variables, but it's still got a lot of stuff in it. So we again try to separate the two variables theta and phi. So we try divide and conquer again. We try a separation y of theta and phi is equal to theta, or capital theta of theta, and capital phi of phi. So we try and separate into a function only of theta alone and only of phi alone. Okay, so again, inserting y equal capital theta, capital phi in for y, doing some rearrangement and some algebra. Again, see the textbook for the specific steps, leads to the separation that looks like this. And here we call these separation constant m squared. So we have this for the theta equation. This combination here is equal to m squared. And for the phi equation, we have it gets pretty simple actually. It's just the second derivative of phi with respect to, of capital phi with respect to phi is minus m squared times phi. And that is basically the equation for a harmonic solution. So the solution to that, which we pick instead of sines and cosines, we pick the e to the I m phi version of harmonic solution. And you can check that if you put in e to the I m phi in for capital phi, that this equation checks out, that you get that this solves this equation. And then something interesting happens because we're dealing with the phi variable, and it repeats because it's an angle which, as you spin around the axis, the function should repeat every 2 pi. So if we add 2 pi to phi, we should get back the same value for the function as we had at phi. And that restricts the values of m that are possible. Because if we solve this, if we set e to the im phi plus 2 pi equal to e to the im phi, we find that e to the I 2 pi m must be 1. And that's only possible if m is an integer, 0, plus or minus 1, plus or minus 2, etc. So this condition on the phi angle and the phi function leads to discrete values, integer values for the m. Okay, so the phi is nicely taken care of. What about the theta over here? So the solution to this is, as you can see, the equation is a little more involved, so it's a little more complicated. Capital theta of theta is a constant, so normalization constant, times a polynomial function, PLM. So it depends both on the L, which was the first separation constant, and the M, which was part of the second separation constant. And this is called the associated Legendre function, this PLM, and it's found from the Legendre polynomials, which solve a certain, which are defined by a certain particular equation. You can see the text for details. And we write it as a function of cosine theta, because this is supposed to be a function of theta, but it's most easily expressed, this polynomial, as a function of cosine theta. So these are some of the functions. P00 of cosine theta is just 1. So the first one is just 1. P11 is minus sine theta. P10 is cosine theta. P22 is 3 sine squared theta. P21 is minus 3 sine theta cosine theta, etc. So they're all, these associated Legendre functions are all fairly straightforward functions of cosine and sine. You might wonder why the sine comes in. Well, you can express sine as the square root of 1 minus cosine squared, and that appears in here. So wherever square root of 1 minus cosine squared appears, we substitute sine just to simplify. These could all be written as functions of cosine, just by expressing sine in terms of cosine. And these are some of the pictures. So P00 is 1. So as a function of theta, it's just a constant. So as we go around, it's a constant. P10 here is right here. It's cosine theta. So it's big here. It's big here at 0. It goes to 0 at pi over 2 and gets big here again at pi. And then there's other shapes. And the higher the indices get, the more interesting and kind of fairly beautiful the shapes get. They're very symmetrical. So these give rise to some really interesting shapes, these polynomials in phi and theta. Sorry, in the theta equation. Okay, so, oh yes. So from the properties of the Legendre polynomials, it turns out that they only make sense from which the Legendre functions are taken. We can only have Legendre polynomials with L equals 0, 1, 2, 3, or 4. That has to do with the definition of the Legendre polynomial. So we have integers for L and only non-negative integers, 0, 1, 2, etc. And then the way the Legendre function is taken from the Legendre polynomial to get PLM, it turns out that M has to, for that process or that formula to make sense, has to run somewhere between minus L and L. Okay, so depending on the value of L, we get some of these integer, we get only certain of these integer values of M are possible. So for example, for L equals 0, M would run from minus 0 to 0. So M would have to be 0 for L equals 0. So we only have, for L equals 0, we only have M equals 0. Whereas for L equal 1, M can run from minus 1 up to, through 0 up to plus 1. So M can be 0 plus or minus 1. Then for L equal 2, it can be minus 2, minus 1, 0, 1, or 2. Okay, and these come from the properties of these functions, the Legendre polynomials and the Legendre functions, which solve this equation here. Okay, so let's go, let's start to wrap up. We can combine the two angular functions into something interesting called spherical harmonics. So the solutions to the angular equation, when we combine the theta and the phi variables, or the theta and the phi functions, are called spherical harmonics. Okay, so, and they look like this. They're written as the y functions because they're the multiplication of the theta and the phi functions, which we had before, which we called y. They're indexed by L and M because those were the two variables involved in the separation constants. You can see the e to the im phi, which was part of the phi function. You can see the associated Legendre function, PLM cosine theta, which is part of the theta function. And then this factor out in front just is a normalization factor to make sure that when we integrate this, it's normalized. Meaning when we integrate this squared over the area of all angles, we get 1. So that turns out to be the right expression for the to make this, when we integrate it over all angles, over the solid angle element, we get 1. So these are the first few, just to give you some picture of this, because this formula again is compact, but it doesn't, it's not simple, it's not easy to visualize. So y0, 0, if we put in 0 and 0, p0, 0 was 1. If we put in 0 for m, this becomes 1. If we put in L and M equals 0, this is 0 factorial over 0 factorial, which is 1. We get 2 times 0 plus 1 is 1. So we just have square root of 1 over 4 pi, or 1 over 4 pi to the 1/2 power. So y0, 0 is a constant. It's the it has the same value in each direction. So it's just like if it was plotted, it would just be a sphere of equidistant from the origin with radius 1 over 4 pi to the 1/2. And then if we look at y10, just look at one more, you can see a couple more. They get, a little more complicated. And for m not equal to 0, we see the phi variable appearing here in the third one. But for the second one, we have p10, since L is 1 and M is 0. That turned out to be cosine theta. So that's why we have a cosine theta here. M is still 0. So this e to the im theta is 1. We have 1 minus 0 over 1 plus 0 factorial. So this is still 1 over 1. Then we have 2 times L equal 1 plus 1 is 3 over 4 pi. So we get a 3 over 4 pi square root. So 3 over 4 pi to the 1/2 power cosine theta would be y10. So it'd be a constant times that that dependence on cosine theta. So it would be big where theta equals 0, and where in big in magnitude where theta equal pi as well, and at where theta equals pi over 2 around the what we call the xy plane, it would go to 0. So it has sort of 2 lobes to it. Okay, so those are the spherical harmonics. And then we're left, so we're kind of done when we have the spherical harmonics with the angular equation. The radial equation, we haven't solved yet. We've just separated it. But we note that it can be rewritten more nicely in terms of the variable u, the function really u, which is r times the function capital R of r. So u is a function of r. When the radial equation, which we saw in the previous slide, is rewritten, it looks like this: minus h bar squared over 2m, second derivative of u with respect to r squared, plus the potential, which is a function of r, plus this term here, which has the L in it, times u is equal to EU. So it resembles the one-dimensional time-independent Schrodinger equation with r instead of x and u instead of phi, except we have this extra term here, which is called the centrifugal term. It has to do with the fact that the particle is moving around in a spherical pattern, and so it tends to fly away naturally. If it was classical, it would tend to fly away naturally from the from the origin. Has to do with the actually the angular momentum of the particle. So this is our equation that we're going to solve. So coming up in the part 2 of the hydrogen atom is we'll be solving this radial equation here for the hydrogen atom potential in for V here, which is V of R is minus E squared over 4 pi epsilon naught 1 over R. So this would be the electron charge minus E times the proton charge E gives us minus E squared. 1 over 4 pi epsilon naught is our Coulomb constant. And then 1 over R is the dependence of the Coulomb potential on radius. Okay, so just summing up very quickly, we saw that the Schrodinger equation generalizes to 3 dimensions pretty naturally, just replacing the second derivative with respect to x with the Laplacian. Then we applied that the time-independent Schrodinger equation in 3 dimensions to a central potential. We got an equation, a fairly complicated equation with the Laplacian and spherical coordinates in it. And then we did 2 separation of variables. The first separated out the angular equation, which we were able to solve nicely in general for the central potential, no matter what the central potential V of R is. And the solution are the spherical harmonics here. And then we were able to rewrite the radial equation in terms of the variable, or in terms of the function U in a reasonably compact form, which we can handle. And we'll look at that next time. Okay, thank you for your attention, and I will see you in class.